for having me here. Pleasure to be here and talk to such an esteemed audience. I think it's really interesting to see just the mix of talks so far, and I'm happy to add to that mix and diversity. So I'm going to talk about robots. And I wanted to think a little bit ahead here, because this is, we're talking industry impact in 5-10 years maybe. So think ahead a little bit, and I'll give you an overview of a set of selective harvesting projects that we have running at the University of Plymouth. It's a talk that's partially from a research point of view, so there's some things that lie far into the future, and some parts are a bit closer. We also run this, we're also looking at hard commercial solutions to drive this towards producers. So first of all, what are agri-robots? Well, big part of agri-robots is this discussion about what happens when you take the person out of the machine. So you have this big agricultural machinery, you take the person out, how does that change how the machinery is operated? When it's running around by itself, does it have to necessarily have the same scale, or maybe it should have the same scale? So there's a real discussion going on there. As you know, there's also one of the reasons we're here is because there's a shortage of labor for, in particular, harvesting. Brexit is part of the discussion, but it's been going on for longer than that, and it's also going on in the rest of Europe and other high-cost countries. So what do we do to get enough people to harvest things we grow? And then finally, there's a pure commercial aspect to this. So the predictions for agri-robots, so we're down here now. We're kind of a few billions. It's expected to grow up to something like 70+ million by 2024, according to some predictions. Other predictions differ. So it's predicted to grow fast because there seems to be a real need, and because there seems to be technology that's starting to get to the right level. So I'm here. There's two roles. I lead a small spin-out company called Fieldwork Robotics. I'll talk a little bit about that, but if anyone has interest in that, they can come and ask me later. And that was spun out from the University of Plymouth, where I lead a lab called the Soft and Adaptive Robotics Lab. So across these two entities, we have, as of this autumn, we have about 15 funded staff and students that I work with. And we develop what's called soft or variable stiffness robots for real-world applications. We started off doing research and education robots. So just sharing with other researchers around the world, and there's institutions in Australia, in South America, and Europe that replicated our designs. We made them open source, etc. And then my real interest has always been the agricultural side, and I think I think agriculture has really come back into the limelight in terms of robotics in the last few years, because we can see that it is actually, compared to some of these other things we've been trying to do in hospitals or in homes, it's actually fairly easy comparatively. So compared to making me a meal and doing the dishes afterwards, picking a tomato seems easier. In terms of funding, we had about 1.2 million pounds over the last 3-4 years. We have a good amount of funding to do this, and we focus on different tasks. We focus on 3 crops right now. One is raspberries. I'll get back to raspberries later. Another is tomatoes, and the third one is cauliflower. Now people ask why in the world would you pick those? They seem very difficult. So raspberries is very complex. Cauliflower is also very complex. And we're one of the things that we're looking at is actually saying, if you're growing a crop for 5, 6, 7 months of the year, what do you do with the robot the rest of the year? So can we look at things that are a little bit more multi-crop, so universal technology that can be revamped and used the rest of the year somewhere else and on something else? And the second thing is, if you go talk to an investor, you want to try to fund your spin-out company in agricultural robotics, then they basically say, okay, if you can solve raspberries, then I'm confident that you can also make something that later can pick strawberries or something like that. So there is this idea that maybe that's a good idea. So we're looking at that, and we're looking at whether from the start this technology could be provided as a service to farmers, rather than having producers try to fund us to develop the technology, which is quite hard for you because margins are very tight, etc. We're trying to say, can we get interest from producers and then go out to private investment and see if they're interested. Okay, so I'll just go through a few of the projects and a little bit about motivation, about why we do the things we do. So first of all, when we talk about selective harvesting in agriculture, we're talking about doing something we haven't done before in robotics, and this is fast manipulation in close proximity to people, to obstacles, in a very complex environment, dynamic environment, and with the sensory data that you rely on, as compared to a factory. In a factory, you don't necessarily rely on a hell of a lot of sensory data to run your robot. It can be pre-programmed because everything is controlled. You take it into the field, you rely on your sensory data. And the big thing there is then that your sensory data will be, it's noisy because of the change in lighting conditions, rain, fog, dust, etc. So you will probably have some collisions with obstacles at some point in the lifetime of your product. You want to try to survive that. It could be wooden poles, it could be close to the ground. You worried about human co-workers. We imagine that robots will not just overnight replace workers in any way. It'll be more like a gradual rollout. And in that case, you'll be working alongside people. So you need to think about that aspect. And then entanglement, etc. So we basically, the short story is that we looked at how the biological systems are built. And we build, just like your arm, you have muscles that act in pairs, and that means that you can move, but also that you can be stiff or you can be loose. So if you have bad sensory data, you can hit something while your hand is soft and you don't break. If you stiffen up, then you can do surgery, or you don't want to have a collision with anything. So we try to take the same concept and put it into a robot arm. So it's called basically a variable stiffness actuator, variable stiffness robot. We designed a robot arm that basically started life as a research platform, but was then transmitted into or moved into agriculture. And we have different versions of it that can do different payloads. The last one now can do a payload of 4 to 5 kilograms. One of the main points of this arm is that it can be robust. So this is an early test long time ago. Just to show that you can, if you have a soft or variable stiffness arm that can vary its softness, as it were, just like your arm. If you're in a soft configuration, you can take abuse. This then led to some projects, and I'll just go through those so you have an idea about what we've been working on. The first one was called, one of the first ones was the China Robot Harvest project we work on in Shanghai, China. We work with one of the top engineering universities in China and a research and innovation platform there. We basically have 4 months to take this robot and modify it for agriculture. That sounds like a very short period of time because we never worked on tomatoes before. But we basically, the whole concept behind this robot is also that it is largely 3D printable. So we're talking about lean manufacturing. We were trying to do some lean innovation here in a sense. We were trying to exploit rapid prototyping advances, for example, to be able to very quickly develop solutions to certain problems. So in 4 months we were able to go to China, in Shanghai, and showcase that we could pick tomatoes at a very crude level, at least. I'll just show you a quick video of that. Sorry about the sound and all that. We had a very excited engineer that wanted to put some cool music on. Yeah. So the technology itself is based on rapid prototyping, just so we can develop new approaches quickly. We can adapt to the variety in the crop that exists, and then we use a set of sensors ranging from extremely accurate tactile sensors, 3D sensors, cameras, etc. One of the key points we really wanted to show was that we could handle tomatoes gently enough. In China, they wanted us to pick it straight off the bush without cutting. But that it was actually strong enough to do that. We shouldn't do that. We shouldn't. We didn't have time to do that. Yeah. So anyway, this was about 2 years ago. So it was the first time we really were picking something in a relatively realistic scenario. You can see the tomatoes hanging from strings because it was out of tomato season in China. But we're going back in January, so yeah. Well, I'll leave it there. So as I said, we're continuing on this. This is an ongoing research project. We're going back. Basically, we're growing tomatoes in our greenhouse on campus in Plymouth right now, and we're going back to China and Shanghai to showcase the new version of it. And really, what we want to do is to move towards a commercialization plan for a full platform. You can see in the lower right corner there, we have a full platform with multiple robot arms on it. By the way, if there are any tomato producers in the room, we're also very interested in moving in, talk to UK producers, because when this project finishes, we will continue in China, but we also want to look at this in Europe. So, yeah. All right. The other application that we are quite keen on is actually raspberries. This is just a lab demo from earlier this year in spring, when there were no raspberries out in the field, and we were basically just showcasing how we approach raspberries. So again, it's the same type of robot technology. It can be soft when it moves quickly. It can stiffen up to be precise. And in this case, it has a different end effector that is able to pick raspberries to a certain degree, at least. So it has a good enough touch sensing. It has good enough finger pads to be able to handle them without damage. And it's got several vision systems that are able to pick out targets, and we're also now moving towards being able to grade them. This looks quite crude, and actually you can see this takes about 12 seconds to pick raspberry. So if we compare it to a person, this is, no, not right now, but it's interesting. If you think about raspberries, 12 seconds per raspberry, we believe we can cut this to 6 seconds within, probably by next season. What does that mean? 6 seconds per raspberry. This platform can operate 24 hours a day, so 3 times longer than a normal person. It would typically have 4 robot arms on each platform, so twice as many as I have. So you already have a factor of 6. So if you compare it directly to a person, it's actually 6 seconds, so it's 1 second per raspberry. But then we also have to think about this as really the only way to compare this is to develop the full business model. And that's one thing that we're working hard on. And it's basically saying, we think we can build a full robot platform like this, just in terms of the hardware. We're talking maybe 20,000, 30,000 pounds for a full robot that can do this. We also believe we can cut that down quite a lot, to maybe half or a third of that. And when you start doing all the numbers, and you then compare per kilogram how much it will cost you, including the people that will take care of the robots, that's when you can start comparing, I think, robotic hardware with people. And that's where that's where you need someone with the industry insight. And that's why we work closely with, for example, Hall Hunter Partnership, which have big facilities here in Chichester. We signed a collaboration agreement with them, and we'll be working with them over the next 2 years to try to develop this technology further. Down on the right here, you just saw a little video of the identification of raspberries, which we're progressing on quite rapidly. So we're able to do that part quite well as well. This also just got funded by Innovate UK grants. So we got 2 years now to work with the National Physical Laboratory, University of Plymouth, and Hall Hunter to develop this towards a full platform. So we're hoping within the next 2 years that we'll have something we can showcase for you. The last project I'll just mention is that we're working with European Regional Development Funding for Cornwall to look at Brassica harvesting. And we went for cauliflowers. We're working with Riviera Produce, a big Cornish producer. CNC Design and Teagle is a strategic partner. This case is a bit more of a recent project, but we are a lot out in the field. We're growing cauliflowers on campus. We're looking at the hard part, which is actually figuring out whether these cauliflowers are mature or not. And we're developing robotic platforms like this one. And you can see that it's early stage, but we're developing a bio-manual platform. So with 2 robotic arms are able to cut and pick this cauliflower, at least the summer varieties for now. We're mainly targeting summer varieties because they don't close up as much as the winter and autumn varieties. Last news is that we're working on the vision systems. We're out in the field, but really we're trying to prepare for next spring. In terms of cutting and grasping mechanisms, that's something I can't show here because it's something that's looking to do patents on. But it is perfectly possible to have robot arms that are just both picking and cutting these cauliflowers quite rapidly. And that's it for me. I think that's the time ahead. Thank you. Yep.